want me to address? Okay. Then if you think of something, let me know. If not, we will continue on here. So the last time we talked about two basic physical laws, the law of reflection and the law of the law of refraction. We'll kind of define what refraction is here. It's also called Snell's law, is the law of refraction. The law of reflection basically says this. The incident angle equals the reflected angle. So the idea is here, you have a ray of light. Remember, we're approximating light as a ray. You have a ray of light that's incident upon some surface at some angle with the normal, always with the normal. We always define everything with respect to the normal. So, or at least in optics. So this is incident upon this surface at some angle of theta. Incident and spin, I don't remember, normal line of strange place. Okay. It's then reflected at the same angle, theta reflected. The surface from which it's reflecting represents a boundary between medium. So you have medium of propagation here. This medium will have some index of refraction. We'll call it N1. 1 is just arbitrary. This is another medium here. This will have some index of refraction N2. Remember, the index of refraction is in some way a measurement of how fast light travels in that medium. Index of refraction for any medium is the speed of light in vacuum, which is really fast, divided by the speed of light in that medium. And I'm going to subscript this with an n to match it with this n, right? So whatever medium has this index of refraction, this is the speed of light in that medium. In any medium besides vacuum and air, we consider those to be the same thing in this course. The speed goes down, so the denominator of this is always less than the numerator. So this is always greater than 1. 1 is the lowest index of refraction. That's the index of refraction of space, basically, a vacuum. We also, in this course, consider it to be the index of refraction of air. But in other media, you'll have higher indices of refraction. 1 is the lowest. And it's a measurement of how fast light travels in that medium, right? The higher the index of refraction, the slower light goes. Turns out the more it bends as well. So I'm showing you the reflected angle at any boundary for a wave, which I haven't drawn a wave, I've drawn a ray, but we have to remember that this is a wave and exhibits wave characteristics. At any boundary, I expect part of the wave to be reflected, I expect part of the wave to be transmitted, right? So the transmission can go two different ways. If this is the path that the light would have taken, I can either bend away from the normal, or I can bend towards the normal. If I'm moving from a fast to slow medium, it bends towards the normal, right? And that's air into anything else. It bends towards the normal. If I'm moving from a slow to fast medium, that's anything getting into air. It bends away from the normal. And in both cases, the angle of transmission is here or here. And to find that, you need Snell's law or the law of refraction, which says N1 sine theta 1 is equal to N2 sine theta 2. And we took from this the interesting case of total internal reflection. Okay. Total internal reflection occurs only when you're moving from slow to fast. And it occurs because as this transmitted ray bends further away from the normal, you get to a point where that ray is traveling parallel to the surface, and it can't bend anymore and still be in this medium. If it bends anymore, it's in the first medium, and that's not transmission, that's reflection. And so that actually happens, right? There is some critical angle for which this line is, this ray is traveling parallel to that surface. Anything past the critical angle then just sends it back into the old medium, you get total internal reflection. Nothing is transmitted. You find that by picking out the transmitted medium and setting this angle equal to 90 degrees, right? That's what that would mean if it were traveling parallel to the surface. It's 90 degrees with respect to the normal. Sine of 90 is 1, then you can solve for the critical angle after that. Okay? So you'll have some homework to do about that. This is reminding you where we are. A couple of other things to say about reflection. We're going to study mirrors and which form images with reflection in the next chapter. We're also going to study lenses, which form images due to transmission in the next chapter as well. But there are a couple different kinds of reflection I want to make you aware of. Two different kinds to be clear. The first is called specular reflection. And the criterion for determining specular reflection is this. If you have multiple rays incident upon a surface that are parallel to each other, right? So this is somewhat artificial, but not too artificial. So we're going to let these rays come in parallel. They all have the same angle of incidence. And when they leave, I should say, they are still parallel. That's called specular reflection. This is the sort of reflection you get from your bathroom mirror, right? Because it's smooth, the rays bounce they mostly remain parallel. I said this is somewhat artificial, but there are lots of systems which we model as the incoming rays as parallel. The rays from the sun are one example. The sun is about 93 million miles away from us, right? So two rays that left the sun at wide angles are not both going to get to the Earth, because after you propagate out 93 million miles, they have separated just a ton. So any rays from the sun, any two rays that get to the sun, get to the Earth from the sun, have to have started out at such a small angle that they're practically parallel. So we model the rays of the sun coming to the Earth as being completely parallel. So when I say this is somewhat artificial, it's somewhat artificial, but not really, because this is what sunlight would look like if you could see it in a ray format. They're all coming in parallel. But in here, this forms images very easily, just because the rays bounce off nice and parallel. The other type of reflection we get is called diffuse reflection. And it occurs when light is incident upon a surface which is not completely smooth. Because light still obeys the law of reflection no matter what the surface looks like. So if I have a somewhat rough surface, which, if you zoom in far enough on any surface, this is what it looks like, right? Even the flat mirror, which we get over here. If you zoom in close enough, it's going to look like this. It just turns out the light we can see, this wouldn't matter for the light we can see. But if you have a surface that looks like this on a large scale, light coming in is going to act a little bit different than this. So you might have a ray that comes in here and then bounces off like that. But next to it, I might have a ray that comes in. I'm going to try to draw these parallel, and then strikes this surface, but in accordance with the law of reflection, it's going to bounce here, and then that bounces here, 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 and you see what's happening, right? So I have light coming in all these different places, even though it comes in at the same angle, it leaves just kind of cattywampus. Diffuse reflection is basically how we see everything, right? I mentioned last time, you can see the shirt that I'm wearing. You can see me because light is bouncing off of me. And then I said, you can't see yourself in my shirt like you can see it in the mirror, but you still see it because light is reflecting off of it and getting to your eyes. This is the sort of reflection that most things exhibit, is diffuse reflection. But this is how we see. We see with both of them. But the majority of how we see is this. This also explains why after it rains, right, and you're driving along a highway, you can see people's headlights reflected in the highway. Because normally a highway surface would look like this. But after it rains, water fills in these gaps and it starts to look like this. Right? So you're actually seeing the headlights reflected off a thin sheet of water that's sitting right there on the blacktop. Just two different vocabulary words with which you should be somewhat familiar. The important thing to know is that for all these interactions, it's obeying the law of reflection. It's just that because the surface has a different shape, it doesn't always look nice and pretty. Okay, does that make some sense? All right. With that said, we can turn our attention back to refraction. So I said I would bring a better laser and a better demo to show you the refraction laser. Now, definitely not a better laser. So this is another piece of blue side. It's a little bit different than the other piece, but hopefully you'll ever see some things. I'll turn the lights off. All right. So you should be able to see that beam inside the blue side pretty well. So the first thing I'll say is I'm bringing the beam somewhat parallel. Let me actually So you can see a couple things pretty well. This is the incident beam. Here's the reflected beam. You can see it on the ceiling. What you're actually seeing is an interesting phenomenon. You see it on the ceiling, it's all spread out. Depending on kind of where I put it, what you're seeing is what's called diffraction. We're talking about refraction in this chapter. We'll get to diffraction in another chapter. But it's spread out for good reasons, basically because the surface of this blue side has been cut with a saw and sanded, but not completely smooth. And so you're seeing some funky stuff up there. But the beam itself you can see pretty well. Like here's the reflected beam, here's the incident beam, and you can also see the transmitted beam pretty well. Alright, now it'll be more obvious when I put this down. You can see the beam kind of bouncing around inside the blue side, I guess. Because at every boundary, we expect part of it to be transmitted and part of it to be reflected. So the part of the beam that gets into the lucite from the top hits this back side, and part of it gets out. You can see it on the desk right here. But part of it is reflected. So at every interaction with the boundary, part of it is reflected, part of it is transmitted. It's also why in the lucite you see the beam getting weaker as it goes down, because at every interaction, the beam is being split. Part of it's transmitted, that carries away some energy. Part of that energy is reflected back into the lucite. But the energy is going to mean, in this case, that the amplitude of this wave gets smaller. And energy has something to do with amplitude. It also has something to do with frequency. But it also manifests itself in the amplitude, which is like the brightness of the wave. Alright, so that's this in a nutshell. And of course, you can see the law of reflection at work here, right? You can see the beam. You can kind of imagine where the normal line to this is. Okay. So that's Snell's law, the law of reflection, kind of in a nutshell. And total internal reflection. Any questions with any of that? Alright. Oh shoot, I'll something in the room. I'll get that in a second. Let's talk about a couple of other things. So as it stands in Snell's law, this index of refraction is medium specific, and that is true. Like the index of refraction of glass is different than the index of refraction of water, of oil, diamond cells, and so forth. So the main value, the main dependence of an index of refraction is medium specific. I'll write it like this. The main dependence of any index of refraction is medium specific. I don't know if that's great English, but that's the idea. There is a small dependence frequency of the incident lights. What do I mean by that? Well, if I look at something like glass, glass has a particular index of refraction. There we go. So I'm going to give you some values to sort of let you see what I mean. Glass has a particular index of refraction. It turns out, though, that if I put different frequencies of light incident upon the glass, they will produce an index of refraction that varies slightly, right? Frequencies for visible light mean color. We all know the spectrum, red, orange, yellow, green, blue. They've taken out indigo for some reason, violet, I don't know why. Each one of those colors represents a different frequency. Now, in a spectrum of light like you get from the sun, that's a continuous spectrum. It's not like this frequency and then this frequency and this frequency. The frequency changes smoothly as you go across, but our eyes are sensitive to certain frequencies and interpret them as being certain colors, right? So we interpret red, we interpret a certain frequency as red color, we interpret a certain frequency as blue, and things of that nature. So where I'm going with this, if I were to tell you, if I were to just look up a problem and say, what is the index of refraction of crown glass, right? You would probably find this value, 1.5, somewhere around. But we can fine tune that a little bit. So if I then calculate it based on specific frequencies, I'm going to get something a little bit sharper. Red light in crown glass obeys the physical laws in accordance with an index of refraction of 1.512. Blue light, 1.514. Yellow light, 1.5. You see where we're going with this, right? So when I say 1.5, that's a pretty good approximation of what the index of refraction of crown glass is. And if we're working problems, we're probably going to say index of refraction is 1.5. Usually when you're working problems in which you care only about how a light bends generally, you're going to use words like monochromatic, which means one color, and give an index of refraction something simple like 1.5. But the real story, that's one of the approximations we make in physics, but the real story is that as any light goes into crown glass or any other medium, it bends in accordance with its frequency. So, what color is light in which all of the frequencies are present? The entire rainbow, what color is that light? If I put all the frequencies in. White, right? Sunlight, basically is what we're talking about. Sunlight is white, by the way. The sun is white. For some reason, we've gotten it into our minds in art that it's yellow, but I promise you it's white. And I can prove it to you. Remind me of your name?
Pierce.
Pierce. Stand up, Pierce, if you don't mind. What color is Pierce's shirt?
White.
White. Now, you can sit down, thank you. Now, if I were to take a flashlight with like a red gel over it, right, for nighttime operations for you military guys, right? And shine that flashlight on his shirt, what color would his shirt look? It's got a red gel over it. What color is his shirt gonna look?
Red.
Red. If I put a blue gel over a flashlight and shine on his shirt, what color is it gonna look?
Blue.
Blue. If Pierce went out into the outside world, what color would his shirt be?
White.
White, right? That's because the light from the sun is white, right? We all draw it yellow, I don't know why. It's even classified as a yellow star. What that means is its output peaks in the yellow to green frequencies, but the light we get from the sun is white. It consists of all of these frequencies. So what happens when I pass that white light from the sun into a piece of crown glass? Well, it bends, right? But not equally. Red light bends a little bit. Blue light bends a little bit more. Yellow light bends a little bit more, and so on and so forth. What that means, here's a beam of white light, and here's some glass, It means that as this light goes in, red light might bend like this, but blue light might bend like this, and yellow light like this. I'm really exaggerating and saying, look, but you can't see what's happening, right? And then outside, it's going to shine on the ground, but I've bent the light. What that has done is it's separated out the colors, right? We know this as a rainbow, and we recognize this as a prism in the cover of Pink Floyd album, right? This is what a prism does. It separates out the light. But how does it do it? It's because these frequencies there are frequency-specific indices of refraction. All in all, we call this the idea of dispersion. And it doesn't just happen with visible light. It happens with all frequencies of electromagnetic radiation. The way electromagnetic radiation bends as it goes into media, it depends on the frequency. It mainly depends on the medium, but it also depends upon the frequency. What that means, of course, is that the speed of these frequencies in the medium are different. And that might make a little bit of sense as to why it disperses. Because if you are walking side by side with someone at the same speed and then one of you slows down a little bit, you tend to drift apart. That's exactly what's happening here. Because the speeds of these frequencies are different, they bend slightly differently as they go to the medium. So this is dispersion. This happens in crown glass. It also happens in water, right? Water has an index of refraction that's bigger than 1. So let's see what happens when, and I'm really going to struggle with these graphics, but we'll do the best we can. Let's say that I have a big bubble of water, not bubble because it's not hollow, a big sphere of water, right? If you want to know how I'm making the water stay into a sphere, I'm a sorcerer, I don't know. But I have this big sphere of water, and I'm going to allow light to be incident upon it from over here. White light. So, what happens? Well, I'm at a boundary. Part of the light is transmitted, part of it is reflected. I'm not going to worry about the reflected portion. It's there, I'm just not going to draw it. But the transmitted part looks like this. It bends, but it doesn't just bend like that. The frequencies, I don't have that many colors of chalk, the frequencies will start to separate out. So it propagates across this big sphere of water to the backside. And I'm at another boundary. Part of it is transmitted, part of it is reflected. This one, I'm not going to worry about the transmitted part. I'm only going to worry about the reflected part. So that obeys the law of reflection. It's going to end up looking something like this. The frequencies are still separating out because I'm still propagating through the medium. And on this side, I get transmission. What have I made? A rainbow. What is this? Well, it's a tiny little water droplet that's suspended in the air after a thunderstorm, right? It's not really a big sphere, it's a tiny little water. I don't think I drew that actually right, but the idea is sound, right? There's dispersion in the water droplet. We see it because it bounces around inside the water droplet long enough to spread out, and then it gets that back outside. Notice though, to see a rainbow, you have to be in a specific location with respect to the sun. Where is the sun? Over here. It's right here. Right? Where do you have to be to see it? And you also have to be looking away from the sun. Rainbows don't, or at least rainbows from atmospheric vapor, don't appear close to the sun. Sometimes you'll get some strange effects from clouds as you're looking closer to the sun. Sometimes you can see little effects in clouds. But this is the big actual bow, right, that goes across the sky after a rainstorm. You see it looking away from the sun. And there's a particular angle, I can't remember, it's 23 point something degrees at which you see it. The reason, though, why you can't really focus on a rainbow, if you ever noticed that, is because this is occurring from all the water droplets from as far as your eye can see, basically. So the water droplets